All right, what happens if so we've been looking at the solubility of these compounds just in pure water. What if I have a compound now where it's not just in pure water? So let's say I want to calculate my molar solubility of calcium fluoride in a solution with, so I don't just have pure water, now I have a solution that has something else. This is called the common ion effect, which means I'm going to see a change in my solubility more than what I would predict just based on my KSP. So let's look what's happening. If I have KF and I want to look at the solubility of calcium fluoride, if I just write that solubility, and my KSP is going to be equal to calcium and fluoride, and that's going to be squared, and I could look up this value. If I have a common ion effect, so I could look at this and say, okay, I can calculate my molar solubility just based on pure water. Let's just do that. We'll come back to what's happening up here. So let's just calculate S first. So remember, I don't care what's happening here with my solid because it doesn't go into my law of mass action. I'm going to assume that I have 0 here. My change is going to be that S. So I'm going to increase by S here. I'm going to increase by 2S here. So for every calcium ion, I'm going to also dissolve 2 fluorine ions. So this would be in pure water. But I don't have pure water. I have a solution that has 0.250 molar of calcium nitrate, and since one of these ions of my ionic compound I'm trying to solvate also has calcium, that's my common ion. So my common ion here is calcium because I have calcium up here. The nitrate's not going to do anything, but the calcium, now I can't start with 0 concentration of calcium because I have some calcium ions already in solution. And so if I have calcium ions already in solution, that's going to decrease my solubility. So I'm going to see my effect here, my change in solubility is I'm going to see a decrease if I have a common ion effect. A decrease, so my molar solubility is going to be even smaller than this. Let's do this calculation. I said I'm not going to do too many calculations with you today, but a few of them. This is 0, but this is 0.250 molar because that's how much calcium nitrate I have in solution. This is a highly soluble compound. So I'm looking at calcium, so my initial starting concentration is not 0, it's going to be 2.25 molar. I'm going to add S to that. This is 2S, this is 2S, and this is 0.250 plus S. Now I can do something here where if my KSP is really small, which it is, and this is fairly high in concentration, so I'm looking at that 10 to the third difference again, then I can do my S is small approximation and get rid of it here. Because even if I add to this, this is so much higher than whatever I would have that I would be adding. It's really not going to change this amount appreciably. So instead of my X is small approximation, this is my S is small approximation. And instead of removing it from a reactant, I'm removing it from a product. So a little bit of a different scenario here. That makes my math a lot easier. Now when I calculate my molar solubility, what you see here is that it has reduced, it's gone down. So in pure water, this would be my molar solubility. This is my molar solubility in 0.250 molar calcium nitrate because these calcium ions that are in that solution are really effectively shifting the equilibrium back to the undisassociated ionic compound here. So common ion effect. You're looking for, does the solution that you have you're adding your ionic compound to dissolve in, does it have an ion in common with what you're trying to dissolve? If it does, it's always going to decrease your solubility.